This week's speaker is Emily Ho from Fordham University's Department of Psychology's program in Psychometrics and Quantitative Psychology. Her talk is entitled Developing New Practices for Increasing Transparency in Social Science Research, an investigation of statistical and psychophysical methods used to detect change. Emily's talk will last between 30 to 40 minutes, after which point we'll take questions from both the audience. You can call in to ask a question on the air at our toll-free call-in line. The number has changed. The number is 1-855-982-9766. Or you can email questions to methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question box that appears on the GoToWebinar control panel. For viewers outside the United States, we recommend using the Ask Question box to ensure that we receive your questions immediately. A copy of the slideshow that goes along with this presentation is available in the Handouts box in your GoToWebinar side panel. Now I'd like to welcome Emily Ho to the IMC. Emily?
Great.
Welcome.
Thanks, Justin, for having me. So today I'll be talking about sort of new methodological advances that I'm in progress starting to develop that hopefully will sort of shed a new light onto this reproducibility crisis that I think not just psychologists, but a lot of other social scientists are starting to have, and sort of the mainstream populace is sort of starting to see. And I should note that this work is done in conjunction with my advisor, David Podescu, who's also at Fordham University. So I'm just going to talk briefly about what you'll be hearing today. I'm going to sort of lay the settings, set the ground for why this is a problem that needs to be addressed, and I'm going to discuss two studies from two sort of different epistemological sort of perspectives on how we're going to address this problem. So first, we're going to talk about theoretical ways of detecting change, sort of discussing significance versus non-significance and ways of doing that. And then I'm going to talk about how people actually determine change, right? Just because something is statistically significant doesn't mean that it's practically significant. And then I'll close with sort of where I hope to go from here. So let's see. So in August of last year, August 2015, there sort of was a lot of press about this article that had started to make its rounds by Brian Nosek, I think, at the University of Virginia. And he found that he did this really amazing reproducibility project, I think with 270 co-authors, and showed that from about 100 studies, only a third of them could be replicated. And that he used a lot of parameters to try and decide what counted as, you know, a study that had been appropriately reproduced. One of them was significance testing, right? With the the p-value was below 0.05, and then he also looked at effect size. And so he found that the overwhelming majority of studies had lower effect sizes the second time around than the original studies that had been published. And so sort of you see here, this is a graph from the paper. I think it's in Science, Nature, and it basically shows that a lot of studies, once you reanalyze them, you couldn't find the same effect size. And not only could you not find the same effect size, sometimes the effect size went in the opposite direction. And so this sort of motivated my thinking. Like maybe he noted in the discussion that there were other ways of evaluating studies, and that these were just sort of a few rough guidelines, right? Like statistical significance or effect size that that he used to evaluate studies. And so I sort of thought that maybe there were other ways of evaluating studies. And I come from, as Justin said, a psychometrics background, and we do a lot of testing on we do a lot of things on a lot of simulation studies. Where we want to assess the effect of empirical distributions, like really weird distributions, on a certain psychological effect. But how this sort of how these distributions are defined are really sort of anyone's guess, and that I think really helps explain why these studies are hard to replicate. Because a lot of these tests, t-tests and ANOVAs and things, they're based on this assumption of normality. normal distribution. And so empirical distributions, which is what I'll call from now on data that occurs, when you when you go into the world and sort of perform an experiment, they're often non-normal, and yet there's no real statistically robust way of measuring the distance between two such distributions. I think oftentimes, we sort of say, well, we perform a Kolmogorov-Smirnov test and just sort of say, well, it sort of passes the test, so we'll let it go. And so, you can imagine if someone comes and tries to replicate the study either by sort of reconducting the same test, that there might be problems due to this. And simulation studies often want to investigate the effect of empirical distributions, which are often non-normal, on a certain phenomenon. And we'll see here that in lots of studies, the way that researchers arrive at, sort of define what non-normal distributions are and the method through which they simulate them are really different, right? So, and I want to make a sort of a caveat and say here that a lot of this sort of discussion also applies to normal distributions, but I think a lot of statistical work has been done on normal distributions, and I think it's safe to say that a lot of data that we collect just simply doesn't meet that criterion, which is why primarily my discussion today is going to focus on non-normality. So we'll see here, the Woods article has a skewness value of 1.57, but then you go to the Savale article down, the third study, and the skewness is 2. And then we have people who operationalize moderate non-normality as one value and extreme non-normality as another. And a method of simulation is also really, really different. I'm only sort of attaching a few of the ones here, but I think the two most commonly used methods, at least for univariate distributions, are the Fleischmann method. I think that's a Psychometrica article in 1978, and just using mixture distributions. And yeah, happy to talk about distributions later on if that's of interest to people. So my goal for the theoretical portion of the work, study 1, was to look at the theoretical distances that people use and see in studies and see how they apply to non-normal distributions. So theoretical distances, I'll explain a sampling of what I mean from there on, I'll explain what I mean later on. So using the Fleischmann method of constructing non-normal distributions, we simulated 107 distributions, which took the form basically of the first mean of 0, variance of 1, and the skewness varied from a negative skewness to a skewness of 1.75, and the kurtosis also ranged. And these values were chosen because the Fleischmann method only works for certain values. I think these were in 0.25 increments, and we'll talk about sort of why it was sort of analytically tractable to use the Fleischmann method, and we didn't want to run into issues of optimization or anything like that. And so I should note, for those of you not familiar with the Fleischmann distribution, the Fleischmann method is that this is a constructed non-normal distribution, so every time you put in the same numbers, you get exactly the same output, which is one thing we wanted. We didn't want to sort of go simulate data that was not replicable, because that would be ironic. Just as an example of what I mean, so what we did was we used 107 distributions, and the values of the skewness and the kurtosis are here in the bottom, the graph, and we compared them to the reference PDF, which is the green line over here. So it was 107 comparisons, and these are examples of what these distributions look like. Some skewed to the right and to the left, and some were leptokurtic, platykurtic, so on. And we used 17 distance measures from 3 classes. So for those of you who are not too familiar with distances, there's a whole sort of encyclopedia full of them. And I just picked the 3 classes that were, I think, the most sort of commonly used in fields like psychology and engineering, things like Euclidean distance and Chebyshev distance, which is in the Minkowski family, and Sorensen distance. And some of these distances just were sort of part of the classes, like an intersection class, and we just sort of wanted to have an exploratory view at how these mapped. So we have 3 classes and 17 measures when we calculated these distances. So you end up with, yeah. So.
Hey, Emily, there's a clarifying question that came in from the audience that I think it's probably best for you to answer now. Are you talking about non-normality of the population distribution or of the sampling distribution?
That's a really good question. I think the sampling distribution.
Okay.
The sampling distribution, but I think that there are certain phenomena that are just simply non-normal. So depending on the question that you're asking, like for example, ability in the distribution is non-normal, but the way that ability is manifested in test scores might be fundamentally. I'm sorry. The ability distribution is normally distributed in a population, but the sort of scale score manifestation of that, like sort of an 800 or a 700 on the SAT, might fundamentally be non-normal based on the decisions that test makers make. Does that make sense?
Well, that sounds like the population distribution, because it's the actual underlying. Because the sampling distribution is that there's a parameter, and then in repeated samples you get a normal distribution. But yeah. What you seem to be saying is that the actual underlying, like if we actually could measure every single person in the population and we got their score, that would be a non-normal distribution. Is that right?
You're right. You're right. Yes, it's population change. Yeah.
Yeah, that came from the audience, but I thought it was kind of a clarifying question. So normally I don't interrupt.
Really good question.
Okay.
Perfect. Yeah, should have clarified that.
Please go ahead.
Okay, so just show you a few examples. So what I would have expected was that I think what we would expect is that the different classes all sort of agree within each other and don't agree across each other too much. And so what we're seeing here is that the Euclidean and the city block distance have a pretty one-to-one relationship, and that as you get further out to like the Euclidean and the Chebyshev distance, that you sort of start seeing this three-dimensional structure, or at least a slight polynomial structure. So that's interesting. We'll spend too much time on that. What's also really interesting is that the LP family, like across all the distances, you see really different relationships within the distances. So. The individual distances. So some of them don't seem to be affected at all by either skew or kurtosis. So that's interesting. And the intersection family sort of shows the same inconsistencies. So what I did here in the theoretical portion is I just pulled out the 3 sort of most commonly used distances, and we'll see that they don't agree too much with each other, and some of them are actually negatively correlated, which is also interesting, I think. This is a rank order correlation, by the way, so not a Pearson correlation. And so what I wanted to do next, after sort of seeing this unexpected result, was just look at the extent to which skewness and kurtosis affected these individual distances. So the intra-class distance measures exhibit pretty little disagreement with each other, and some measures seem to just be completely unaffected by skew and kurtosis. And I wanted to see whether there was a way to group these distances based on their sensitivity to skewness and kurtosis. So I conducted, I suppose, 17 polynomial regressions, so 17, one for each distance within the 3 classes, which basically regressed skewness and kurtosis, their polynomials, and then their interactions with each other. And so I'm going to show you 2 things. First, I'm going to show you what the prescribed taxonomy is. So the blue is the Minkowski family, the red is the LP family, and the last one, the purple, is the intersection family, and just sort of to see what the results are. And so the 1 and the 0 just simply means significant or not. The actual values are quite vary. They have different ranges, so it's not meaningful to compare. And so what we see immediately is that there's, within the different classes, within each class, the skewness and kurtosis affects the distances sort of asymmetrically. They don't all sort of have the same form, which is what I would expect given that they're in the same theoretical classes. And in fact, in some of these, especially in the intersection family, the skewness and kurtosis is completely unaffected. So that's interesting. And I should add all of these computations were done on the probability density functions of the distribution. So, and then so what I did also then is I wanted to rearrange the taxonomy of these distances based on what was predictive. So for the first cluster, skew and kurtosis, the polynomial kurtosis and the intersections were the ones that were the statistical features that predicted distance. And then in the second family, I think it's only the skew and the skewness squared, and kurtosis is completely unpredictive, and so on and so forth. And so we see here, this is interesting, and I'm not, I think, yeah, I'm happy to hear your thoughts as to what, where we might go from here, is that there's clearly this different grouping that is revealed when we apply these very theoretical distances to non-normal data that completely belies the theoretical groupings that we sort of, have come to expect. So, and some of these don't agree at all. So I see that I think the Chebyshev is the one that sort of stands in a class of its own and is predictive of everything except for skew and kurtosis. Yeah, so the summary of study 1 is that theoretical distances don't exactly map onto these non-normal distributions the way we would expect. Distances, in some cases, completely disregard these moments, so it doesn't matter whether these moments are heavily skewed to the left or right. The distances just aren't picking up on them. And so these theoretical distances are sort of, the way that they're manifested don't properly reflect the process that by which they're generated. And so, and a variance explained taxonomy, variance explained meaning R squared, of distances reveals pretty radically different groupings than the theoretical classes. And so what I wanted to do next, I think, and I'm happy to hear thoughts on this, is maybe if we examine different distance classes or different ways of producing non-normal distributions. There's sort of a whole suite of ways using combinations of different distributions that you could produce, stranger distributions that are non-normal, that extend beyond the first 4 moments, as well as using different statistical features such as tail weight. So my second question was, now that we've sort of seen the statistical judgment aspect, I wanted to see how well human judgment can discriminate between differences in distributions. And so there was a study published, I think, in the Journal of Risk Communication, or the Journal of Risk and Uncertainty, by, I think, Nick Thomas et al. In Cardiff just this year, which asked 6 experts what their assessment of the sea level rise was in 50 years, or I guess now 35 years. And so using 2 display formats, each one of these experts basically came out with their own CDF, and that was the elicitation method that produced the CDF. So what I did was I used 2 display formats, cumulative distribution functions and probability density functions. And we asked laymen to evaluate the perceived distance between the experts. So in study 1, we sort of have the statistical distance, and now we have sort of a human distance. We sort of wanted to see how that compared. And so the experiment display looks something like this, where on the left you have CDFs, and on the right you have PDFs. And these are the same experts, expert 1 and 2. And on the bottom here, the participants were asked to evaluate the difference between, basically, use the slider bar to judge whether, how far it was to extremely different or to identical. So, and we didn't ask them anything beyond this, like we didn't ask them for certain features, like, which features do you think are, they agree on, right? So this is a very general sort of, very general study. And so then we performed, well, first we performed multidimensional scaling on these distances, on the distances that these people gathered, and that yielded basically a very univariate linear structure. So we just scaled it down to a unidimensional scaling, and we applied these the three theoretical distances: the Euclidean, Sorensen, and the wave's edges. And we then looked at the PDF and CDFs. And we see here that what's really interesting is that the theoretical distances here, in this case, agree. They agree pretty, pretty well. And the PDFs and the CDFs sort of see moderate agreement. And so display format definitely influences what people are thinking, but using the PDFs, So the theoretical metrics agree on the clustering of expert judgments, and so we'll see the first, the Euclidean, the Sorensen, and the wave's edges all pretty much agree with each other. And at first I thought it was maybe a precision error, maybe we were being too precise, like, the experts were giving us judgments that gave us, 7 points on a CDF, but, we really did, 9 or 11. And I tested this on a lot of varying levels of precision, and the results are pretty much the same. But we'll see here, what's really interesting is that the human judgment aspect of it, regardless of whether you're looking at the CDF or PDF, is that they don't seem to agree with the theoretical distances at all. So human judgment is sort of tapping onto sort of a completely different, they're sort of picking up on completely different features of these distributions than the theoretical ones are. And even across display formats, it's the same data, the CDF versus a PDF, the same people show really moderately different judgments. So that's interesting, I think. So my conclusion is just that theoretical metrics perform non-uniformly when assessing the extent of systematic deviance from a standard normal distribution. But then this effect disappears in the empirical study when we found high agreement between theoretical metrics and pretty moderate agreement between empirical judgments based on PDFs and CDF display formats, but low agreement between, or basically no agreement between empirical judgments and the theoretical metrics. So I think the sort of next step is what I want to do is replace the expert opinions with the distributions that we produced in the first study and sort of see where things go. So those are the references, and for those who are curious, the theoretical distance formulas for these three are here, and the P and Q are just one of the points in the PDF. So the ith point in the PDF. I think that's it.
Okay. Thanks for that presentation, Emily. At this point, Emily's available to take questions from the audience. You can call in to ask a question at our toll-free call-in line, 1-855-982-9766. You can email questions to methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question box that appears on the GoToWebinar control panel. For our viewers outside the U.S., we recommend using the Ask Question box to ensure that we receive your question immediately. I'm going to start off with a question that maybe reflects my own ignorance, but I sense that probably a lot of the audience is going to have the same question. So you started your talk off by mentioning replication and failure of many papers' results to reappear when the analysis is sort of repeated by a different team. But then the rest of your paper was about judging that's basically the mathematical or statistical proximity of two distributions. And I'm not sure what those two things have to do with one another. So can you explain how all the things you talked about, proximity, the proximity of certain non-normal distributions to normal distributions has to do with the replication crisis?
Yeah, so I think that's a really good question. I think that there are not enough ways or not enough tools in sort of the psychological or the method in the toolbox of people to be able to evaluate and compare studies across each other. I think sort of the tools that we have currently, statistical significance, like effect size, sort of only start to get into that, and that given that a lot of the distributions we deal with on a day-to-day, given that a lot of the distributions we deal with in sort of our experiment and analyses have to do with non-normal distributions, it seems to me sort of obvious why a lot of these reproducibility projects see such low success rates, because there aren't enough tools that help us sort of more robustly evaluate the actual change that is happening, sort of like a P. I guess what I'm saying is that statistical significance is sort of limiting, and that a lot of the data that we use in everyday deal with these non-normal distributions that aren't being appropriately evaluated. I guess that's sort of where I'm coming from with
well, so I'm thinking of, it's been a while since I read the article that you cited at the very beginning, but I remember that the basic sort of set of studies that they were looking at were, lab experiments for the most part, where you like these priming experiments where you give people a cup of hot water or a cup of cold water and then see whether that changes their warm or cold feelings toward someone else in some sort of prompt situation, things like that. And when you're doing that kind of experiment, or any kind of experiment that involves a sort of treatment control condition, what you're evaluating is the difference in means, right? You might be doing it the regression, but you're evaluating, okay, I'm measuring some response in group A, I've got a response in group B, I want to see if those responses are different. And I think that an implication of the central limit theorem ought to be that the difference between those two things, the sampling distribution of that difference ought to be normal. So that's the basis on which t-testing and z-testing are built. So I guess what I'm wondering is, and that's what people are getting at a lot of times when they're talking about replication, because, well, if you have an underpowered study and you look at 20 different treatment effects, then one of them is going to come up significant just by chance. Yeah. So what I'm wondering is, why is it that we need to, I'm hoping you can explain why we need to worry about non-normal distributions when the central limit theorem tells us that these differences we're interested in ought to be normally distributed.
I think that there's a lot of, but first I think that's a really good question. I think that lots of times we assume that there's normality when there isn't. Perhaps the reproducibility crisis, that particular article wasn't quite pertinent, wasn't exactly maybe the right article to lead in with, but I think the general idea is that a lot of meta-analyses and a lot of sort of aggregation studies, such as the reproducibility project, come up with these sort of weakened results. And I guess one of my questions is why, right? If we assume that it's all not normal and everyone's sort of doing their job right, why is the problem? Why is there such a low success rate? And I think part of it is because a lot of these distributions actually aren't normal. That even if you collect a lot of data, the underlying distribution of a lot of these things aren't normal. And maybe that's an assumption I need to think about and rework.
Well, the thing I was thinking about is, I think it depends on what you're measuring. So if you're measuring, think about the most simple regression, right? You've got a binary treatment variable, and you're modeling regression with y equals x. X is or t. T is either a 1 or 0, and then there's a beta on that t that tells you the treatment effect. That beta, if the true beta, if there is a true beta, in other words, if there's a real parameter out there, then the sampling distribution of that parameter, the central limit theorem tells us ought to be normal, right? We have all sorts of theoretical results that tells us that the sampling distribution of that beta ought to be normal. And so in that sense, I'm not too worried about non-normality, because it doesn't really matter what the underlying distribution of the error term is even. The error term doesn't have to be normal in order for at least in large samples, for the distribution of beta to be normal, although in small samples it might make a difference. But if you're trying to measure, maybe it's the case that effect is not constant. Maybe it's the case that the true beta actually takes its own distribution, and that distribution is non-normal or something. Then there might be something to worry about. But I guess I'm just really, because what I'm confused about is I was under the impression that we could count on the normality of these parameters we were interested in. And now what I'm hearing from you is, well, no, we can't count on that. We need to think about comparing this true distribution, which is non-normal, to our assumption of a normal distribution. And I'm trying to make sense of that, and I'm having trouble. So that's what I'm trying to figure out. I'm trying to have that explained to me, in other words.
Yeah, I mean, maybe something that maybe wasn't made so clear in my study is that I think one of the nice things about the work that I'm doing is that there doesn't need to be this assumption of, like, we don't, like, sort of, if you have sort of a nice way of assessing the distances between distributions as sort of an exploratory way, sort of exploratory framework, then in a way statistical tests are not so important. I'm not saying we don't use them. I think we should definitely use them, but I'm saying that this might provide sort of a nice guide into why a lot of these studies aren't replicating. That this is sort of a hint as to, like, well, maybe if distances aren't sort of showing what they're supposed to be showing, like over studies and studies that a distance is picking up on different parameters of a distribution, then maybe that's part of why these studies aren't replicating. Yeah, well, that's part of the. Yeah, sorry. I think that's part of a theoretical sort of cornerstone that I need to think more about. But I'm not sort of arguing against the central limit theorem. That's not that's not what I'm trying to get.
That would either make you very, very famous or very, very wrong.
Well, I don't. Yeah, I'm not saying it's super controversial here. I think. I'm just saying that there are different ways of assessing differences between distributions. Statistical tests are one of them. Effect sizes are another, and this is sort of a beginning of a stream of research that says maybe there's another way to describe differences.
Well, let's think about. I mean, maybe it's helpful to think about this in very practical terms. So suppose I see a real simple lab experiment. It's done in the literature. I think. I suspect that might just be a spurious relationship, or no, it's not spurious. I'm sorry, but that might be a relationship that is attributable to chance. They just basically got noise, and I replicate their study, and I get some new results. So how would I apply what you're talking about in your paper today to comparing my results to their results?
Well, let's see. I think that. Based on all the sort of theoretical distances that I came up with, I think that we would look at the distances that sort of tapped into the statistical features that were most important. So, for example, maybe a theoretical question that you have in your study is, makes certain assumptions about the distribution of the data, and applying this certain distance, like maybe we saw that the Chebyshev distance is very good at picking up on the skewness and kurtosis, then we'd apply that distance. But we know that applying another distance would not yield any results. Does that make sense a little bit?
Well, I was thinking, I was just looking for something much more, I suppose, basic. Like, I've got some, I've got a treatment effect that I found. I've got a treatment effect that they found.
Yeah.
I've got standard errors for both of those, I assume. What do I do with those bits of information to compare the similarity of the two findings using using what you've developed?
Let's see. I'll be honest and say I don't have a strict answer for you right now, but that the sort of work that I'm doing sort of starting to lead into certain best practices for which distances we could use that would be more illuminating than not. Does that make sense? I think that, like, for example, in your study, if you just ran a t-test, you might just show, oh, the differences are significant, and you move on. Or you might find that, let's say, the differences aren't significant, in which case your study contradicts the other study. But then where would you go from there? Like, as a researcher, where would you go from there? And I'm saying where you would go from there is to try and apply some of the theoretical distances that I'm starting to think about.
I would guess that, I think probably if you want to stay down this, if you want some unsolicited advice, if you want to stay on this, the track of thinking about replication, I think it's going to be really helpful to have an application, just something that explains, here's what's going on, right, and here's how I would do things differently, and sort of just lay it out in I mean, the point is not to embarrass somebody or prove somebody wrong. The point is just say, here's how a normal replication, the way we do it now, would go, and here's how I think it really ought to go, and here's how you get differences. Because the way it's explained now, I can't speak for everyone, of course, but it just doesn't connect with the idea of replication to me.
Sure.
I do think that the idea of different distance metrics might have lots of different applications in other areas. So, for example, if we're thinking about measurement problems, I think the idea of trying to figure out how measurements are similar or different from one another is very important, and what you're doing would have immediate application to that. Maybe that's already been done, I don't know, but I'm just...
Not a lot, yeah. Mm-hmm.
Okay. But for the specific area of replication, I think it would be very helpful to just have a, sort of, here's what we would do, here's what someone else would do in a real apply study, here's what I would do, and then here's how the things are different.
Okay, yeah, that's really helpful. Thank you. I'll have to write that down. Yeah.
All right, well, we're a little early, but there aren't any questions from the audience, and so I don't see any reason for us to sit and stare at each other for 20 minutes. So I want to first thank Emily for giving her talk today. Thank you very much. I also want to advertise next week's talk. Next week on Friday, the February 19th at noon Eastern, we will have a talk from Rocio Titinik. I probably pronounced that wrong. I'm sorry, Rocio. From the University of Michigan. Her talk's entitled New Developments in the Analysis and Interpretation of Regression Discontinuity Designs and Their Application to Political Science. And I hope you go to our website, www.methods-colloquium.com, to register for that talk and to get more details, and I think we have an uploaded paper for her too. So thanks again, Emily, for your talk this week.
Thank you.
I will see everyone next week, I hope. See you later.